Welcome to lecture 7. In this lecture we will teach you how to reduce a given matrix to a particular form called row reduced echelon form by using elementary row operations. So first let us define what is a row reduced echelon form of a given matrix. So given a matrix, we use elementary row operations. Just recall what are the elementary row operations. First, exchange of two rows. Second one, multiplication of a row by a non-zero constant. And the third operation is replace the given row with the row plus a scalar times another row. That means add a scalar multiple of another row to a given row. So these are the three elementary row operations. Now what is a row reduced echelon form? The first non-zero entry from the left in a non-zero row of a matrix is called a pivot, and we denote a pivot by putting a box around it, just for convenience of notation for you to understand. We do this, we put a box around the pivot. A column where a pivot occurs is called a pivotal column. A matrix A of order m by n is said to be in row reduced echelon form if the following conditions are satisfied. Each pivot is equal to 1. The column index of the pivot in the I plus jth row is greater than the column index of the pivot in the ith row, and this is true for each j bigger than or equal to 1. That means the column index of the pivot in the I plus first row is greater than the column index of the pivot in the ith row. So if you have a pivot in the ith row, the pivot in the I plus first row will be on the bottom right of the pivot in the ith row. Third one, in a pivotal column, all entries other than the pivot are 0, and all 0 rows are at the bottom. If a matrix satisfies all these 4 properties, then we say that the matrix is in row reduced echelon form. Let's look at an example. The first matrix that is given there, 1 2 0 0 0 1 0 0 1 0 0 0 0 1 is in row reduced echelon form. Now let's look at the second matrix that is not in the row reduced echelon form. Why is that? The first pivot is the entry 1 comma 2, that is 1, and all other entries in that column, pivotal column, are 0. Now let's look at the next pivot. Next pivot is in the second row, but the pivot is 2. So therefore this is not in the row reduced echelon form, because each pivot must be 1. Similarly, we leave it as an exercise for you to understand why each of the remaining 3 matrices are not in row reduced echelon form, and then apply elementary row operations and bring them to row reduced echelon form. So that can be done. We will explain you how to do that. After that, you come back and do elementary row operations on each of these matrices which are not in row reduced echelon form and bring it to row reduced echelon form. So how do you reduce a given matrix to a row reduced echelon form? We describe here an algorithm. So this is written in algorithmic style. So first, set the work region R as the whole matrix. That is the matrix that we are starting with. If all entries in R are 0, then nothing to do. All those 4 properties are satisfied, and hence it's in row reduced echelon form. If there are non-zero entries in R, then find the leftmost non-zero column. Mark this as a pivotal column. Now in that column, find the topmost non-zero entry. In that pivotal column, find the topmost non-zero entry. Suppose it is alpha, then that's a pivot. Draw a box around it. Now if the pivot is not on the top row, then do a exchange with the top row of matrix A and bring the pivot to the top row. If the pivot alpha is not equal to 1, then replace the top row by 1 by alpha times A. 1 by alpha times that row. Now by using the elementary row operations, by adding appropriate scalar multiple of each row to the first row, bring all entries in that column to 0. So therefore now we have 1 on the first row and 0 in the remaining column, in the remaining entries of the column, and if there are rows on the left, all of them are 0. Now look at the submatrix on the right bottom of this pivotal entry. If there are no such submatrix exists, then stop. We are done with it. Else, take that submatrix. On that submatrix, apply the same algorithm. That means you go back to step 2. In that submatrix, if all entries are 0, then again we stop. If all there exists a non-zero entry, keep going. Keep going to steps 2, 3, 4, and so on, and then move to the next submatrix. So this is how you bring a given matrix to a row reduced echelon form. Let's do one example. So we start with this matrix with rows 1, 1, 2, 0, 1571, 1545 and 2879. So here our job is, the first step is simple. Find out the first non-zero entry, that is non-zero itself. So we don't have to do any row exchanges. Now one is pivot, the first pivot. Next, our job is to bring all the entries in that column to 0. So we do that operation. O1 is the set of elementary row operations. R2 is mapped to R2 minus 3R1, R3 is mapped to R3 minus R1, and R4 is mapped to R4 minus 2R1. This brings to the this makes all the other three entries in that pivotal column 0. Now we restrict our attention to the column, the submatrix with rows 2, 1, 1, 4, 2, 5, 6, 3, 9. So in that, let's mark the first non-zero entry, that is 2. Now this we need to, that's a pivot and it is not equal to 1, therefore we divide it by 2. Divide the row by 2 and we get the matrix. The submatrix will be 1, half, half, 4, 2, 5 and 6, 3, 9. Our next job is to make all other entries 0. That means in that column except 1, all of them should be 0. So let's do the elementary row operations. We change R1 to R1 minus R2, R3 to R3 minus 4R2 and R4 to R4 minus 6R2. Now all the pivotal entries are all the entries in the pivotal column are 0. Now the next non-zero entry in the 2 by 2 submatrix on the bottom right of the second one is 0, 3, 0, 6, and that non-zero entry is 3, and that is non-zero. Therefore first that is non-zero and that is not equal to 1. Therefore our first job is to make it to 1. So divide it by 3. Divide that row by 3. Now do the next set of elementary row operations on the other entries and get all other entries in the pivotal column to be 0. So replace R1 by R1 plus half R3, R2 by R2 minus half R3 and R4 by R4 minus 6 R3, and the resultant matrix is the matrix with rows 1, 0, 3 by 2, 0, 0, 1, half 0, 0, 0, 0, 1 and 0, 0, 0, 0. Therefore this matrix, now we don't have a submatrix on the right and all the bottom entries are 0. Therefore the algorithm stops here, and you can see that this satisfies all the 4 properties that we have mentioned in the beginning. So this matrix is in row reduced echelon form, and if you collect all these row operations that we have done, you can see that the row reduced echelon form is obtained by a series of matrix multiplication by several elementary matrices. So we have given the product here, you can verify that. Let's look at one example here to show that if you have two matrices A and B, the matrix multiplication and taking the row reduced echelon form, these two processes do not commute, in the sense that you multiply A and B and then bring it to row reduced echelon form. At the same time, you bring A to row reduced echelon form, B to row reduced echelon form, and multiply. These two may not be the same always. We have a very simple example. A is matrix with rows 1 0 0 0 1 0 0 0 0, and B is the matrix with rows 1 0 0 0 0 0 and 0 1 0. The row reduced echelon form of A is itself. Row reduced echelon form of B is you exchange the second and third row. Therefore, AB will be 1 0 0 0 0 0 0 0 0, and that is in row reduced echelon form. But now, if you multiply the matrices RREF of A and RREF of B, what you get is another matrix that is in the row reduced echelon form, but it is not equal to the row reduced echelon form of AB. So with this we conclude this lecture. We will do row reduced echelon form and some of its application, in the future lectures.